All right, so today we're going to do the second sample midterm. And so that covers chapters 11 and 12. And then, of course, on Monday, we're going to go over the sample final, which is 13 and 14. So, all right, let's get that open. Sample midterm number two. Now, again, there's fill-ins here. You may have already taken the first midterm and you can see that there are some short answer questions in there, although they're in the form of multiple choices. It's not exactly the same thing, but still, you do need to remember all these definitions. So there's nothing here will go to waste, but the actual test doesn't have fill-ins as such. All the questions are either well, technically, they're all multiple choices, but some of them require calculations and some of them do not. So, but these types of questions you're seeing here could show up in the form of multiple choice questions. Okay, so for example, one key property of the chi-square distribution. All right, now there's actually a few that we went over, but you can pick one. So, in other words, if you were taking this test in the classroom, you would only have to provide one. Having said that, we'll go over them all. Okay. All right. So, first of all, it is continuous. And by the way, let me just draw a little sketch here to remind you what it looks like. Yeah, so this is going back a ways. Let's fix that. That's not bad. All right, so here's your chi-square distribution. And there's a few key things to notice here. First of all, it is continuous, which means, of course, it is not discrete like the binomial and the Poisson. Number two, it is only defined for um, non-negative values of x. Okay, in other words, it can't be negative. It could be zero or it could be positive. So we use the word non-negative to include both zero and positive. It is skewed to the right or positively skewed. And number four, it is characterized by degrees of freedom. Okay. Now, of course, the T distribution was also characterized by degrees of freedom, but in a different way. Okay. Because the chi-square distribution is defined in terms of the standard normal and the number of terms that are used to create the chi-square distribution represent the degrees of freedom. Okay. Anyway, number two, it is, oh, well, kind of gave it away with that one. Um, the chi-square distribution is derived from what probability distribution? That would be standard normal or Z. And if you remember, this is how it works. Okay, so in other words, you can see we've simply added up the sum of squared um, standard normal random variables, and the number of them determines the degrees of freedom for this distribution. Okay. Number three. Well, the answer is right here, but um, when testing hypotheses about the variance of a population, what is the critical value for right tail test? All right, so this is what they're getting at here. If you remember, unlike the t in the standard normal, the chi-square distribution, we always consider the right tail instead of the left. So when you're looking up values in the table, this is how we write it. So alpha is the area in the right tail. And that this is, of course, our rejection region. But the area is alpha. That's the key. And you notice it's in the right tail. All right. Just the opposite of what we saw with the standard normal and the T. All right. Number four. When testing hypotheses, all right, here we go. When testing hypotheses about the variance of a population, how are the degrees of freedom computed? Okay, well, that's easy. In fact, you can see it right here. This n minus one right here is meant to represent the degrees of freedom. Of course, this is the tail area. And then the second term is the degrees of freedom. So for this type of application, it's simply n minus one, which of course is the sample size minus one. All right, number five. What is the name of the test that is used to determine if a population follows a specified probability distribution? All right, so that would be goodness of fit. Good. Now, number six. When testing hypotheses about the independence of two populations, how are the degrees of freedom computed for the critical value? So you may recall that this is the one where our critical value looks like this. So the degrees of freedom, well, first of all, this type of test is always conducted as a right tail test. That's because of the way the hypothesis is set up. Remember, it's independent or not independent. And that means that this is a right tail test. But the degrees of freedom over here refers to the table that you were given with all the data. And so remember, these are the rows, these are the columns in the data table you were given for this problem. And so the degrees of freedom is R minus one times C minus one. By the way, this table is sometimes called a contingency table. Okay. All right. So whatever data you were given, and we'll see one of these when we get to the problems. Whatever the data looks like, not including the totals, of course, the data itself is organized in rows and columns. And so the number of rows minus one times the number of columns minus one is the degrees of freedom. All right. And then up here, I'll just label this. All right. What else do we have? Number seven. Is the chi-square distribution defined for negative values? No. Okay, it's that simple. And you can see why, because of the way it's defined. It's the sum of squared terms. It cannot obviously be negative. All right, number eight. When testing hypotheses about two population variances, which probability distribution is used for the critical value? Okay, so that would be the F distribution. All right, so chi-square is used for one variance. F is for two. All right, number 9. All right, here we go. When conducting hypothesis tests about two variances, is the test conducted as a right, left, or two-tailed test? This is another one of those cases where it is automatically run as a right-tailed test. Oh, sorry. No, wrong one. This one can be any one of them. Okay. Then 10, which probability distribution is characterized by two different kinds of degrees of freedom? That would be F. We have the numerator and denominator degrees of freedom, which is very unusual. You don't see that every day. Two different degrees of freedom. And that's again because of the way it's constructed. If you remember, it's the ratio of two chi-square random variables, each divided by its degrees of freedom. And therefore, this becomes the numerator, degrees of freedom. And of course, that means this must be the denominator, degrees of freedom. All right. So now we're ready for the problems. All right. So first we have, all right. So this is a two-part problem. All right. A soft drink company wants to ensure that each 1 liter bottle of its orange juice is filled correctly. The maximum acceptable standard deviation is 0.02 milliliters. Okay. If the standard deviation exceeds this standard, a change will be made to the bottling process. All right. Now, that means we're looking for hard evidence that the standard deviation is above 0.02. And we could write it that way. But normally we write these hypotheses in terms of the variance. So we're going to write it like this instead. So if you take out your calculator and you square 0.02, you'll see that it's 0.0004. So just to be consistent, we're going to write it in terms of the variance, even though it was worded as a standard deviation problem. It is the same thing. So we'll just follow along and we'll convert these into variances. By the way, when you type this into your calculator, you might notice something interesting. When you square 0.02, it comes back not with 0.0004, at least mine. It comes back with 4e minus 4, which means 4 times 10 to the minus 4, which in turn means 0.0004. All right, what else do we know? We're going to test this hypothesis at the 5% level. So let me just copy these down here one more time. Variance, the null is that the variance is less than or equal to 0.0004. And the alternative is that it's greater than 0.0004. All right, now for this type of problem, the test statistic is pretty straightforward. Now it says in the problem that they took they have a sample of 30 bottles, and they discovered that the sample standard deviation is 0.018. All right, so we start plugging in all these details. Now keep in mind, make sure that you square this because this is a standard deviation, but this calls for a variance. In the denominator, this is the hypothesized variance, which is 0.0004. Don't square it again. Okay. So when you put these into your calculator, 2349 is what I got. Now, as much as we'd love to use the p-value approach, the calculator doesn't actually have what we need for that. So instead, we're going to use the traditional test statistic critical value approach. So the critical value is, okay, so just like we saw in the fill-ins, with this type of test, the degrees of freedom is n minus 1. The right tail is the alpha. Okay, so here that would be zero point zero 0.05 and 29. So we're going to look it up in our table. Yeah, I've got so much stuff open here. Here it is. So remember how this one works. It says right here as a hint, right tail area. Remember, the chi-square only considers the right tail, the opposite of the standard deviation and the t-distribution, where we always look at the left tail. So we need to know two things. Degrees of freedom, 29, and the right tail area is 5%. Where do they cross? Right there, 42.557. But our test statistic is only 23.49. And so, of course, that means we do not reject the null. which is good news because no change needs to be made to the bottling process. All right, remember, they were only going to do something if the standard deviation was above zero point zero 0.02 or the variance was above 0.0004, but that didn't happen. Now, for part B, we'll do a confidence interval. Now, if you've forgotten what that looks like, I have a list of formulas here somewhere, or you can look it up in the slides. And here it is. Oh, sorry, wrong one. We're looking for the variance. You could, in principle, do a confidence interval for the variance or the standard deviation. But here we're going to do the variance. All right, so let's plug in the numbers. Now, by the way, this means we do have to look up some new critical values. Also, if you notice too, when you write the chi-square random variable, the standard procedure is to write the alpha, or the tail rather, as a subscript. Um, Most books don't also put the degrees of freedom, but I think it's easier this way. It's just so you don't lose track of what you're doing. All right, so this one, we can look it up in the table now. The right tail area is 0.025 with 29 degrees of freedom. Oops, what happened? Uh, all right, I don't know I'm going to open it up again. There it is. All right, so this time we're going to need a different column header. So far we've used 0.05. Here's 0.025, but with the same number of degrees of freedom, that gives us 45.722. Oops. Oh, what just happened there? Well, somehow it decided to move it. 45.722. All right, now for this one, in this case, 1 minus alpha over 2 is 0.975, combined with 29 degrees of freedom. Oh, okay, it's over here. All right. So this time it's the same row, but it's this column here. And that leaves us with 16.047. All right, we have everything else, so we'll plug them in. So S squared is 0.018 squared. Then we divide by 45.722. Over here, the numerator is the same, of course, but now we divide by 16.047. All right, so let's see what that turns out to be. All right, now again, it's scientific notation, but that's because this is a variance. Um, so just remember, just as a quick tip, yeah, so these are the same thing. So here's a bit of a rule of thumb. I don't know if it helps you or not. When you have a negative exponent like this, you see that four there? That means there's one less or three, what we call leading zeros. And that's where we get 0.0002055. And then over here we have, all right, 5855 with again three leading zeros. Now, um, if you needed a standard deviation, you would just take the square roots of both sides. Okay. So in other words, the square root of 0.0002055 is approximately 0.014, and the square root of 0.0005855 is approximately 0.024. Yeah, that's close enough. So that would be our confidence interval for the standard deviation. Okay, either one, they basically mean the same thing. All right, so that one's done. So what's next? Oh, I just realized it does actually say standard deviation, so we're good. So that means the correct answer is this one. All right. So number two. Ooh. So this is clearly going to be, you notice how it says observed and expected frequency. That means this is a goodness of fit test. All right, so pension fund wants to determine if the mean returns to its investment portfolio in 2025 follow their historical distribution, which would be here. And then the observed would be whatever we're seeing this year. And so basically what they want to know is if what we're seeing this year follows what we've seen in the past. Okay. So it's a goodness of fit test. All right. So we're going to run this test. Um, I did, if I remember correctly, I showed you the shortcut for this. What you're actually doing is this. So the null is that it does follow the historical distribution. The alternative is that it does not. All right, alpha is 0.05. Now you remember this test statistic. It looks pretty scary. So remind the way this works, this is observed. Now, each of these columns is actually known as a category. The subscripts, for some reason, they use J for this. That's just standard notation. It could have been I guess, or K, but and the E is the expected. And of course, this is the same thing. So you can do this by hand if you want. Maybe we could do that once just to see how it works. All right, let me copy this down here. And then I'll remind you how the shortcut works. All right, so we have here F1, F2, F3, and F4, E1, E2, E3, E4. Oh, sorry, not over 2, 11. All right, so this one isn't that complicated. We can do this by hand once, just to remind ourselves how this works. I've got 2.2182. Now, for the chi-square distribution, that's a very small number. Oh, you know what I just realized? No, there's a problem here. The second and the fourth ones, I left out a zero. Yeah. Oops. This is why we don't like to do it by hand. I just noticed it now. So it's even going to be smaller than that. It's not nine, it's oh 09. All right, let's try that again. Yes. Okay, what happened here? I noticed, all right, that's better. Okay, all right, so let's try that again. 0.3333 plus 0.0909 plus 0.0667 plus 0.0909. Um, okay, that looks a lot more like it. 0.5818. Well, that's not just small, that's minuscule for the chi-square distribution. So it's very, very unlikely that we will reject this null. But let's remind ourselves how to do this with the calculator. Let's do this. So we're going to have to turn these rows into columns. The observed frequencies are 4, 10, 14, and 12. That can be our list one. And then for the expected, we have 311, 15, and 11. So we'll enter these in our lists. L3, when we're done, we can come back here and enter this into a formula. And I'll remind you how in a second. Oh, wait, sorry, that's 2, L2. All right, so first let's just enter these numbers into the lists. Now, for the list for column 3, where we have um, yeah, we're going to put a formula here that replicates what you see right here. And the way to do that is to go to the header, and then you're going to type exactly what I tell you. All right, don't change anything. Open paren, second L1. So in other words, second one, minus second two, close. Oh, sorry, we forgot the square. Divided by second two. Okay. Uh, all right, I did something wrong. Hold on. Okay. Now, if you do that, I'm getting 0.3333, 0.0909, 0.0667, and 0.0909, which we recognize as what we have up here. Now, by the way, how do you ask for the sum in a case like this? What you have to do is stat calc one for one var stats, enter list three. So in other words, if it doesn't already say list three, you type second three, then go down to calculate. And somewhere in there, um, oh wait, maybe not. Oh yeah, there it is. It's number two. Okay, but it turns out that there's yet another way. So in other words, rather than entering a formula into list three, you can go to second vars, scroll down, and what do you know? Right there. Oh, I'm sorry, it's not vars, it's stat. Second stat. Nope, just stat. Just plain old stat. Stat tests. All the way down. Letter D, chi-square, goodness of fit test. Enter. And we want it to say observed L1, expected L2. Now, here, unfortunately, they threw us a curveball. The degrees of freedom, we have to tell it that. So if you look at your data, um, you'll see that for this one, it's very simply K minus 1. Now, if you remember, we were given four columns of data. These are four different rates of return. So there are four columns, four categories. K is 4. And if K is 4, the degrees of freedom must be 3. All right, so you hit that, then calculate. Whoops. Now, if you notice, it's not giving us the critical value, but it is giving us a p-value. It's giving us the test statistic and the p-value. That's it. All right. Now, of course, if you go way, way back to the beginning, alpha is 0.05. Yep. And that means do not reject the null, which was the population does follow the historical distribution. Now, what if you wanted to use the test statistic critical value approach? Whoops. What would you get for your critical value? All right, so this is one of those tests that is always in the right tail, and we have 3 degrees of freedom. We go to our table. Here's column 0.05, 3 degrees of freedom, 7.815 is our critical value. But our test statistic, if you remember, was really tiny, 0.58 something. So, of course, our conclusion is do not reject the null. All right. So you see, we've got a lot of options with this one. You can pick the one you want. All right, but the bottom line is that just you need to recognize that it is, in fact, a goodness of fit test. We're comparing certain data that we just have to some specified distribution. It could be coming from historical experience, it could be from some of their assumptions, it could be anything, but it has to be made clear to you. Here's the data we have, and here's what we're comparing it with. And we want to know, does one follow the other? Okay, so that makes it a goodness of fit test. Beautiful. All right, what is number three? Aha. So what's going on here? A researcher at an investment bank is analyzing the risk of Apple stock and Tesla stock using the variance of the returns as a risk measure. So they want to know if the variances are equal. So we're testing a hypothesis about two variances, and it's a two-tailed test because we just want to know if they're equal or not. So for this one, the test statistic, see now this one we have to be careful because we're using the F distribution. So let's take a look at the data they're giving us. We have Apple and Tesla. For Apple, we have 10 years worth of data. In other words, 10 observations. Sample size is 10. And we have a sample variance of 0.09. For Tesla, we have 12 years, and the variance is 0.16. Okay, now, when you're using the F distribution, though, here's something we have to remember. First of all, the F statistic is written like this, but we have to make sure that whichever population we choose, or sample we choose, the variance of this first sample has to be larger than the second. So that means we can't leave it like this, because if you notice, Apple's variance is smaller. So therefore, we can't let the naming convention stay. What we have to do is this. This has to become N1 and S1 squared. Actually, I can leave this right here as long as we label it correctly. And over here, this becomes sample two. Okay, because this is the only time we've ever seen this. Usually it doesn't make any difference which population or sample is which one. Here it makes a great deal of difference. We have to ensure that whichever one we call S1 squared is larger than S2 squared. So therefore, Tesla must be the first sample and Apple must be the second sample. That's one of the quirky things about this test that you don't see with our other tests. This is unique to this case. Other than that, it's pretty straightforward because now all you have to do is substitute 0.16 over 0.09 It's approximately 1.78. Okay. Now the critical value will be, so here's our numerator, degrees of freedom, denominator, degrees of freedom. Now this is alpha over 2 because this is a two-tailed test. Otherwise, it would be just alpha. All right, great. So N1 is 12. So that means we have 11 numerator degrees of freedom. N2 is 10. So we have 9 denominator degrees of freedom. And of course, alpha over 2 is 0.025. So we haven't used this table in a while. Let's review how it works. First of all, we must use the 0.025 table. Remember, there's a separate F table for every possible tail area. And in fact, I happen to have all three of them right here. Well, what do you know? There's the right one. Now, the other thing to watch out for is the across the top. This is the numerator degrees of freedom. These are denominator. Do not get them backwards, otherwise you'll get the wrong answer. Okay. So it's 11 and 9. So let's read across the top for 11 and down for 9. Now I can't see the label over there. 9 is this row. 11 is here. So therefore, it's 3.91. But our test statistic was only 1.78. So, of course, our conclusion is that we do not reject the null, that the two variances are equal. And that's it. We're done. We just like with the chi-square, we don't have the ability to do a p-value from our calculators. They don't have that information. So here we're just going to use the traditional approach, test statistic, critical value. All right. I think that's all of that one. Yes, it is. Now here's the test of independence. So ExxonMobil is conducting research to determine if the preferences of its customers are similar throughout the United States. A sample of customers is randomly chosen from the North and the South. For each one, they ask if the customer prefers grade 87, 89, or 93. And there's that contingency table. And that's how we know, one way we know that this is a test of independence. And we're going to test the hypothesis that the preferences are independent of geographical region, or they are not. Right? Alpha is zero point zero 0.05. Now, this is the one where we enter our data into a matrix. Okay, because otherwise the test statistic would take a very, very long time to calculate by hand. So luckily we have the technology that makes that unnecessary. So here's what we're going to do. Enter not the totals, but the rest of the data into matrix A. How do we do this? All right, here we go. Second, X inverse. And you got all these matrices sitting here. I'd like to edit matrix A. So move across to edit, enter, and then you'll have matrix A in front of you. Now, if it doesn't already say 2 by 3, you can just type over it. Remember, 2 rows, 3 columns. All right, if it already says 2 by 3, that's fine. Sometimes it does. All right, but if it doesn't, just type over it and then enter the data into that matrix. All right, so let's take a minute and do that. All right, now you can hit stat, tests, and the one you want is C, chi-square test. All right, now once you get there, here's what you want it to say. All right, if not, you can change it, but this is what we want. And it's going to come up with a test statistic. And a p-value. And so in this case, the alpha was zero point zero 0.05. So you can see this one's a bit of a close call. Okay, now if you felt so inclined, you could now solve for the critical value and decide based on that. And this is the one we saw earlier in the fill-ins, the degrees of freedom. This is at R minus one, C minus one. So again, if you come up here and look at the data, you can see there are two rows and three columns. R is two, C is three. So we come back down here. And so we have, and that turns out to be, so this is two times one, which is just two. Okay. So if you look at the table, not that table, here it is. We need 5% in the right tail with 2 degrees of freedom, 5.991 right there. Well, it's refusing to let me highlight it, but there it is, 5.991. But the test statistic, as we saw, is 5.891. So even though it's close, it doesn't count. So we do not reject. Okay. So no, the reason why the p-value is so close to zero point zero 0.05 is because the test statistic is getting really, really close to that rejection region without actually reaching it. It's close, but it's not quite there. So we reject the null anyway, no matter how close we get. If we're not actually in the rejection region, we do not reject the null. Beautiful. All right, what do we have next? So this is a two-parter. All right, so we want to know if the variance of the dollar amount of internet advertising is greater than zero point zero 0.04. If so, the company will increase the amount it spends on internet advertising. So this is a simple variance. So we're not using the F distribution. This is for chi-square. So let's start writing this out. They're looking for evidence that the variance is greater than 0.04. So the null would be everything else less than or equal to 0.04. And then they're telling us the alpha is 0.05. Also, they're telling us that we chose a sample of 20 websites and the sample variance is 0.0625. All right. So the test statistic, based on the chi-square distribution, is this one. We have 20 minus 1. Now here you got to watch it because it says s squared here. This is s squared. Don't square it again. 0.0625. And the hypothesized variance is 0.04. All right, so what does this give us? It's 29 point, let's try that again, 29.6875. And the critical value? Uh, yeah, right tail. Okay. All right, we go back to our trusty table for 19 degrees of freedom this time. So it's right here, combined with the right tail area of 5% is going to bring us right here, 30.144. All right, so what does that get us? And of course, the test statistic is 29.6875. Again, it doesn't quite reach. It's very close again, but it's not in the rejection region. So we do not reject the null, that the variance is less than or equal to 0.04. So therefore, we do not. I think they were going to increase their advertising. Hold on. Yeah, okay. Do not increase spending on internet advertising. All right, and again, we don't have the ability to do a p-value. So we have, this is it. This is the only option we have. Now there's a part B here, if I remember correctly. There it is, 95% confidence interval. This time it's for the standard deviation. So let's do it. And like I said, there's formulas in the slides. I happen to have a list of them right here. We'll use this one. All right. Now we do have to look up some values in the ta table. So once again, alpha was 0.05 and the sample size was 20. So we look this up in the table. The header will be 0.025, the area in the right tail, with 19 degrees of freedom. Right here, 32.852. And now this one will be um, the tail area will be 0.975 combined with 19 degrees of freedom. That's in this column. 19 degrees of freedom gives us 8.907. All right, now we can fill in the rest. The sample variance was 0.0625. Actually, I'm going to run out of room. Let me just move this. And now we just do the calculations. By the way, don't forget to take the square root. It's easy to do that. All right. So that is our confidence interval for the standard deviation. All right. So let's see what's next. Now, whoops. So the corporation organizes their data into the following. Well, I think we're looking at a goodness of fit test here. All right, let's copy this in. So yeah, I mean, this is nice, this setup here, but we've got 40 states in which this corporation does business, and they want to know Okay, so the sales are across the top. These are the three categories, and we're going to have observed, which is current, and expected, which is historical. And we want to know if the current data matches the historical data. Okay, right. Okay. So again, either they do or they do not. So this is a goodness of fit test. So what we're going to do is enter this data into our lists. All right. So what do we have? 10, 25, and 5. And for L2, the expected is 8, 30, and 2. All right, let's start with that. All right, and just like last time, go to stat tests and pick D, goodness of fit test. Make sure it knows that observed is L1, expected is L2. Now, degrees of freedom is K minus 1. Here, there are only three categories or columns, and therefore, degrees of freedom is 2. All right, so we come back with, we have a test statistic, and we have a p-value of 0.054. All right. We keep having all these close calls today. And so since alpha was 0.05, So, of course, the null was that the population follows um, the historical data. Now, if you wanted to, you could go look up the critical value. So remember, it's 2 degrees of freedom. On the table, you would see 5%, 2 degrees of freedom, 5.991. And of course, our test statistic doesn't quite reach that far, 5.833. So once again, this tells us do not reject the null. Okay. All right, I think there's one more. Let's see what we have. Nope, two more. Let's see what this is. All right, a researcher wants to determine if the variances of two manufacturing processes are the same. We have process A. We have a sample of 10 years of data, and the sample variance is 0.05. And for process B, we have another 10 years worth of data, but this time the sample standard deviation is 0.06. And they want to know if they're the same, which means it's a two-tailed test. All right, alpha is 0.05. Now remember, with two variances, the test statistic is based on the F distribution, and that means we have to be careful. We got to make sure S1 squared is greater. Oh, no, they're backwards again. All right. Well, that means we have to fix it. So in other words, S2 is larger than S1. We can't have that. So we're going to reverse these two. Okay, now we're fine. So that means zero point zero 0.06 squared over zero point zero 0.05 squared. 1.44. What about the critical value? All right, so remember, this is the one that has two different degrees of freedom. And what are they? N1 minus 1, N2 minus 1. So in other words, this is what it looks like. Oh, I just realized something. You know what? I didn't read it carefully. These are variances. So that means that here I have to fix this. Whoops. Yeah, you got to be so careful with this. Sorry about that. Yes. So yeah, we have the labeled correctly, but these were not standard deviations given to us. They were variances. So the F statistic is not 1.44, it's 1.2. The critical value will look like this. It is a two-tailed test, so alpha is cut in half. The degrees of freedom are n1 minus 1 and n2 minus 1, respectively. Alpha is 0.05. Both of these had a sample size of 10, so therefore we end up with both the numerator and the denominator degrees of freedom are, oh, wait a minute, no. This is supposed to be cut in half. Yeah, they're both 9. All right, so we go get the table. Remember, there's one table for each. Alpha. In fact, it's this table. You can tell because right here it says alpha. And so we need the intersection of 9 degrees of freedom in the numerator. And we already have here from the last problem 9, this is the denominator degrees of freedom. And where they cross, they give us 4.03. All right, then. But our test statistic was only 1.2. So therefore, we do not reject the null, that the variances are equal. All right. That's it. We're done because there's no p-value available to us. And then finally, one more, and then we're done. Um, what is it? All right, this is a independent, it looks like it's the independence test. All right, so we have the data from the three models made by Tesla, and all the customers were asked, would you buy this car again or not? Okay. So what we want to find out is if the proportion who will buy again is the same for all three models, which is equivalent to saying, um, are the two independent, meaning whether you repeat buy it or not, and which model you have, are they independent of each other? Okay, so what we're going to do is enter the data, not with the totals, into a matrix. All right. So we could write the hypothesis in the following way. Um, oh, you know what I just realized? This is not what I was expecting. You know what it is? Because they said the magic word is proportion. So in other words, it's not an independence test. Instead, it's the test that all three proportions are equal. So in that case, um, oh, you know what? Well, here's the tricky part. This test is equivalent to saying that um, purchase preferences are independent of model. So the test for three or more proportions is the same thing as the test of independence. So in other words, we are going to enter this into a matrix. Now, technically, this is what it's asking us to do, but this is the equivalent to what you're seeing here. So in other words, we're just going to do the same thing to find the test statistic and the critical, the p-value, enter the data into a matrix, specifically two by three, because that's the data we have. So we'll do that by hitting second inverse. And then, of course, now from that earlier problem, matrix A is already two by three. So you don't have to change the dimensions, but you have to go over to the edit button so you can enter the new data. And here's the data. And then you hit stat tests. And then again, you're going to pick C, chi-square test. All right, enter. Now this is the one where you need to tell it observed is A, expected is B, all right, here we go. So the test statistic, 9.909, p-value 0.007. So we reject the null that all three proportions are equal and accept the alternative that they're not all equal. And again, if you just love the critical value approach, so this is what you would have to do. R is in this case 2, C is 3. Let me just double check that. Yeah, 2 rows and 3 columns. And, we looked this one up earlier. It was 5.991. And so our test statistic is 9.909, which puts it well into the rejection region. And that, of course, means, once again, reject the null, that these are equal, and accept the alternative that they're not. All right, so that's it. Oh, that was a lot, but now we're experts in these chapters. The second midterm should be a breeze. All right, so just keep in mind, it's not due until August 3rd. You can take it whenever you want to, but just be aware that you only get one shot at each question. But you don't have to do it all at once. You can save your answers and go on and work on it again. But ultimately, everything is due on August 3rd. Okay. So Monday, we're going to have one last session where we go over the sample final, and then we are completely done with everything. but I'm still available for online Zoom sessions or emails if you need them. All right, so I'll post these when I log off, and I'll see you tomorrow night.